Welcome to Lesson 1-2. Today we're going to talk about the scientific method. What separates science apart from other ways of thinking is the fact that we use experimentation to gain and organize our knowledge. So, for example, religion, you'll pull the concepts of religion out of maybe religious documents and religious teaching, but you don't necessarily have experiments that organize that knowledge. And so, in order to be considered science, you're basically collecting data from some type of organized experiments. Scientific method is what kind of leads us to the scientific inquiry, and in the scientific method, there's usually steps that are involved. Those steps don't have to be linear like you probably were taught in elementary and junior high school. In order to practice scientific method, first you need to make an observation. That observation can be something like, why is that weed growing over there? Where did that weed come from? Then you generate a hypothesis. I think the wind carried that weed there. Then you run some type of experiment. And so the experiment we'll talk about in detail later. But then if the experiment supports your hypothesis, you can come up with a theory, and you can make a prediction and do more experimentation. And that theory is going to continue to be modified as technology improves and ways of thinking improve. So going back to those steps, to make observations, you can make two different types of observations. You can make a qualitative observation or you can make a quantitative observation. Qualitative observations do not involve numbers. And so if you were to make a qualitative observation, you might say something like, the sky looks more blue today than it did yesterday. To make a quantitative observation, you need a number and a measurement unit, and we'll talk about measurements in Lesson 1-3. Once you've made that observation, then you generate a hypothesis. A hypothesis is simply an explanation for that observation. A lot of students are hesitant to generate hypotheses because they feel like they don't know the answer to the question, so how can they generate a hypothesis? A hypothesis is just a bold statement. You made an observation, and this is why you think that observation occurred, or that observation what's behind that observation. Third step, you perform an experiment. To perform an experiment, and this is often the hardest thing for beginning scientists, because they cannot develop an experiment that's going to test their hypothesis. So what you need to be very careful that your experiment is repeatable. So you need to be able to list out the steps so that someone else could repeat it. You also need to make sure that in your experiment, the only variable that's changing is the one that you intend to change. So for example, if you were wondering what's the perfect amount of water for a particular plant, then you want to make sure that you're keeping everything else the same. You're keeping the amount of sunlight the same, the type of container, the type of plant, how you're measuring, and so on. And you want to make sure the only thing you're changing is the milliliters of water you're adding to each particular container. And so you do need to be careful on that, because you want to be able to say that what you were changing was causing the change in the experiment. If you follow through with your experiment and it supports your hypothesis, then you have what you call a theory or a model, and that's just basically an explanation of something that happens in nature. So why does this behave a certain way? Why did that plant end up growing there? Well, because the wind carried it there, and that would be a way that nature behaves. You might find another reason that plant happened to be there. Maybe the dog stopped by or something like that. So that's how theories are developed. They're just basically having evidence that supports your hypothesis. A lot of students get confused between law and theory. A law usually is a summary of observed behavior that is always there, always manifests itself. So, for example, on this slide, it tells you about the law of conservation of mass, and that says the total mass of materials is unaffected by chemical change. So, therefore, when they say that's a law, that means they've seen that time and time again, and they continue to see that. This next particular slide shows us the difference between law and theory. With a law, that's a statement of generally observed behavior. So there are a lot of laws in physics. law of gravity, so on, summarizes what happens. A theory is based on a human invention, and it's attempting to explain why something happens. So, for example, the theory of evolution is considered a theory because it's attempting to explain why something's happened. And a theory is not necessarily wrong, it's just using the best of the scientific evidence we have at the time. Will the theory of evolution ever become a law? Most likely not, because the things that are proposed in that theory, no one was on this planet to observe. And so that's kind of the difference. Laws are just observable time after time after time, and theories, there's a lot of theories out there, and there's nothing wrong with a theory, as I mentioned earlier. If you do focus on a theory, that might limit you, though, to how you look at things again. So, if let's say global warming, that's a theory. That's something that hasn't been observed time and time again. It's a theory that we're using to legislate things. However, if we look at that and then perhaps there's evidence that doesn't support it or supports something else, if we're so focused on that, we might not be able to see that alternative explanation. Just recently, if you've ever heard of the Tacoma Narrows Bridge collapse, most of you are probably too young, and in fact I wasn't around when that happened either, but in that Tacoma Narrows Bridge collapse, it was a suspension bridge built over a wide cavern, and it lasted about 4 to 5 months, and it collapsed. And a lot of scientists said, oh, it's because the wind was rushing under it, reached the resonance frequency of the bridge, and caused the bridge collapse. That was accepted for years and years and years and years. In fact, most of us taught that in our science classrooms. They now know that it was not due to resonance that bridge collapsed. It was due to something called the flutter effect, which actually happens a lot of times with airplane wings. So, if you limit yourself and you say, okay, resonance is the theory, that's what it was, then you will ignore the other evidence, and that gives you a prejudice. And so you do have to be careful of that. Other things that cause prejudice, it could be a profit motive, could be the fact that you don't have a budget. Is lead harmful? Well, no, lead's not harmful, so you're going to just dispose of this down the drain. So you do, obviously that's a very bad example. You do have to be mindful of that. Fads, wars, religious beliefs, all those things can affect how we look at those theories and cause us to refuse to accept other evidence. Again, another critical thinking question, and you are more than welcome to stop on that and ponder that. The last slide just takes us back to the observation section and the difference between a qualitative and a quantitative observation. Which of the following is an example of a quantitative observation? Quantitative meant it had a number and a unit. The only one that has a number and a unit is answer choice D. Note that C says substance A has a greater mass than substance B, indicating there's a number involved, but it does not specifically give a number. That concludes lesson 1.2. We're going to move on to measurements in lesson 1.3.